Hello everyone. Welcome to this lecture on integral approximation using simulations. In this lecture, I'm going to talk about uh, Monte Carlo approximation to a finite interval, also Monte Carlo approximation on an infinite interval, and also variance of the estimator that we are going to use, and the advantages and disadvantages or limitations of this method. So, why do we want to approximate an integration using some simulations? That is because there are lots of situations where we have to evaluate definite integrals or indefinite integrals, which are difficult or impossible to evaluate analytically. So in that kind of situations, Monte Carlo simulations provide an alternative numerical approach based on random sampling. So there are other methods, of course, mathematical, numerical approximations using numerical methods. What I am going to discuss in this lecture is how to use a statistical idea uh, to get an approximate value for an interested integral. So the main concept that we are going to use here is law of large numbers. You remember we discussed this law of large numbers as a particular example of almost sure convergence in a previous video. So this method that we are going to discuss today relies on the law of large numbers. What does law of large numbers basically say? It says that the sample mean converge to the population mean. Or more statistically, if you mention sample mean converges to the expected value of the random variable when the sample size increases. So that is the basic idea of the law of large numbers. So what is the practical use of it? The practical use of it is actually if you have a reasonably large sample, you can use the sample mean of that sample as an estimate for the population mean or for the expected value of the corresponding random variable. So that is the idea that we are going to use here also. So what is the method? If I explain it very briefly, it's like this. The basic idea is to express the integral of interest. Suppose I want to uh, find out the value of some integral, and suppose I denote that by capital I. What we are going to do is we are going to express the same expression as the expected value of a function of some random variable x with a known probability function simple fx. Right. So the first step is to express the uh, integral of interest as the expected value of some function of a random variable capital X whose density function is known. Then if the integral of interest is equal to some expected value, then according to the law of large numbers, we should be able to get an approximate value for that using uh, the sample size. sorry, using the sample mean with a large sample, right? So that is the idea that we are going to use, right? So let me explain it again. There is some integral of interest we denote by I. We are going to write down the same expression as an expected value of some function of a random variable capital X whose density function is no. Then, according to the law of large numbers, we should be able to approximate that I as the sample mean of that function uh, when the sample size is large. So if I explain the same idea mathematically, I can write it like this. Suppose we want to find out this integral. Let us call it I. Right now, notice that for a if fx is some density function of some random variable. Suppose fx is a known density function, right? And then we can write down this integral as this. What I have done is multiplied by fx and divided by fx. So this integrand is the same as this one. Therefore, this integral is the same as this. But now, because fx here is the density function of some random variable x, you will see directly that this expression is actually the expected value of this quantity here as a random variable, right? So this is actually the expected value of g of capital X divided by f of capital X. So that is coming directly from the definition of the expected value of some function of a random variable. Now comes the law of large numbers. So according to the law of large number, this should be approximately equal to the mean of sample mean of this quantity here. That is the quantity that we are looking at. So if you consider this as one random variable, then have a random sample of observations, simple x1, simple x2, simple x3, up to simple xn coming from this density function. Then we can calculate the sample mean of this function using those observations, simple x1, simple x2 up to simple xn. So that is the quantity that I have written here. Is the sample mean of this function of x, right? And that should be approximately equal to the expected value according to the law of large numbers when n is large. So that is the basic idea behind this Monte Carlo approximation. Right? So now Monte Carlo approximation to an integral general. Right? Now we are going to look at this in two parts. First, we will look at how to find out an approximation for this kind of integral when a and b are finite, both a and b are finite. And secondly, we will look at when at least one of them is infinite, right? For example, 0 to infinity, negative to infinity, positive to infinity, that kind of indefinite integers, right? Okay, so now we look at the first situation, Monte Carlo approximation on a finite interval. Suppose we want to evaluate the integral I, where it is the integration of some function gx from a finite value a and a finite value b. Now, in this kind of situation, now remember the method that what we are going to do is we are going to select a suitable density function of some random variable x. The important thing is that the support of that density function should be the same as the limit of integration, right? Otherwise, we will not be able to write down this thing as an expected value of that random variable, right? So if you have a finite interval like this, an easiest density to select is in a finite interval is the uniform distribution. So let us suppose that there is a random variable x, right? We just consider a random variable x, which is uniformly distributed on this particular interval a to b, the same as this limits of integration. And then the density is, of course, given by 1 over b minus a. Right. So if I just follow the same procedure, I can write down I as uh, gx times b minus a divided by b minus a. In other words, this is actually the same as gx divided by fx times fx, right? Fx is equal to 1 over b minus a. So when you say gx divided by fx, b minus a comes to the front, right? Uh, Integration over x. And there you can see this is actually, so this is the density function of a uniform distribution in the interval AB. Therefore, directly we can see now this is actually the expected value of this quantity, b minus a times g of capital X, right? This is when you integrate it, we write down in terms of the variable of integration x here, but of course, when you consider the expected value, it is the expected value of b minus a times g of capital X, where capital X is uniformly distributed in the interval a to b. So then, by the law of large numbers, this expected value should be approximately equal to the sample mean of this quantity, this new random variable, based on a large sample. So what we are going to do is, first, we are going to consider a very large sample uh, of simple x1, simple x2, simple x3 up to simple xn, where n is very large, from the uniform distribution from A to B. Then we can calculate this quantity for each xi and then take the mean of those values. So that is, I can write down, I can take this b minus a out of the summation, b minus a. This is actually the mean of those gxi values, 1 over n, I from 1 to n, gxi. So the law of large numbers says that when n goes to infinity, this becomes this quantity. What is important to us is if n is large, this quantity will be approximately equal to this one, which is the integrand of interest, integral of interest. Right. So what we are going to do is take a random sample, very large sample, for example, 10,000 values, or if possible, even more than that, and then calculate gxi, that g for whatever the gx interested, and then take the mean and then multiply by b minus a, and that will be giving you a good approximation to I. So let us look at an example. So here it says when n is large, I should be approximately equal to the sample mean of those values. So let's evaluate this quantity from 0 to 1. I want to integrate log x over 1 plus x with respect to x from 0 to 1. Right. So you can see that the limits are a and b are finite here. So we can easily use the same method that we used earlier, described earlier. Take the density as a uniform distribution from 0 to 1. Right. So if I apply that method here, b is equal to 1, a is equal to 0. So I'm taking the data x1 up to xn from a uniform distribution from 0 to 1. And then my gx will be this quantity here, log x divided by 1 plus x. So for each x, I will be calculating this quantity and then take the mean and then multiply by b minus a, in this case, 1 minus 0. Right. So actually, in this case, it's possible to get the exact answer. And that's a good thing because we can compare our approximate value and the exact value. Exact answer is going to be, in this case, negative pi square over 12. Of course, as a numerical value, it will be approximately this value up to 6 decimal places. So we'll take this as the actual value, exact answer. Right? So now let us use the Monte Carlo approximation to get the answer. Right? So I have written down a few R commands for this. I'm going to take a sample of about 100,000 in this case. It's not that difficult, right? So my A is equal to 0, B is equal to 1. So what I'm going to do is, first of all, take some X values, 100,000 X values from uniform distribution. So that is taken by R unif. N is the number of observation, minimum value is A, maximum value is B. So in that interval A, B. So then I'm going to calculate gx at each of those simple xi values. So I call it capital G is equal to log x divided by 1 plus x. So this capital X contains 100,000 values. Capital G contains corresponding gx values. So according to the previous formula here, I will be equal to approximately B minus A, and then the sample mean of those G values, right? So I'll say I hat. I call it I hat because this is not the exact I. It's going to be an estimate, right? So I hat is equal to B minus A times mean of G, right? So this is the answer that I get when I call for I hat, and I have written as that. So you can see that this is the approximation that I got from this particular sample of 100,000 I got, and it is 0.8227, so approximately 0.883. So what was the answer that I had here? Uh, yeah, it's also 0.8824, right? 67. I got here 0.8827. So you can see that's pretty close. Right? Very, very good enough. I think for most of the practical calculations, this will be good enough, right? So you can see that it gives you a very good approximation, right? Let's look at another example. In this case also, we are considering an integral over a finite interval, but the function is a little bit complicated now. It's quite difficult to evaluate this integral analytically, very difficult. Uh, but we can do it using this Monte Carlo method. So let's say A is equal to -5 here, B is equal to 5, and then e to the power. This whole thing is our gx, simple gx, right? So here also I can use the uniform distribution as my fx. That is the easiest thing to do in this case. Right. So if I go through the same procedure, n is still 100,000. My A is now -5, B is equal to 5. I'm generating random numbers from this A to this B, this A to this B, not from 0 to 1 now, right? And then calculate Gx, uh, at each of those x values, and then I hat is going to be B minus A times mean of G. And in this case, my answer is 1.42425, right? And actually, I got this answer using an online uh, integration uh, platform. I got a very close answer in that case. They were using some numerical methods, not the Monte Carlo method. So using the numerical method, the answer is very close to this. But as I mentioned, this is very difficult to evaluate analytically. You'll have to use numerical method, completely mathematical, or this kind of statistical idea. Right. So those two are the examples of using Monte Carlo approximation to get the integration over a finite interval. Now let us look at an integration, how to evaluate an integration over an infinite interval, like from negative infinity to positive infinity, or maybe from 0 to infinity, like that. Here I'm considering the integration from negative infinity to positive infinity, but it can be from 0 to infinity also, right? So now it should be clear to you now, in this case, we cannot use the uniform distribution in a finite interval as our density function. right? Because uniform distribution is always in a finite interval. So instead of that, we can use any other density function which has the same support as this limit here. So in this case, we'll have to consider a density function. If you're considering integration from negative infinity to positive infinity, we'll have to consider a density function which is going from negative infinity to positive infinity, like a normal distribution, for example, OT distribution. That kind of distributions are suitable. But if I is from 0 to infinity, for example, in that case, you will have to use a density like a gamma distribution, exponential distribution, any density you can use theoretically. But of course, there is some thing that you have to be careful a little bit. I'll talk about that at the end. But theoretically, it can be any density function. Our fx that we select can be any density function in the corresponding interval. Right. So we select, theoretically, we have to select, in this case, if you are considering integration from negative infinity to positive infinity, you have to select a density function which satisfies this expression, right? The whole area under the curve should be equal to 1. Right. So then we can write down I as the same thing that I mentioned earlier. I is equal to this. You can divide by and multiply by fx, then you get this. So this is actually the expected value of g of capital X divided by f of capital X. So by law of large numbers, this should be approximately equal to the mean of this quantity when the data are coming from the corresponding density function, right? So that is the idea I have explained. Actually, in this case, we call it, this whole method is called importance sampling also. Importance sampling. Right. So it's Monte Carlo approximation using importance sampling. This method of selecting a suitable density function and then applying this again and again, of course, is the Monte Carlo simulation we call Monte Carlo simulations. But the method that we use here is called the importance sampling. So the density function that we select as fx is called the importance density or proposal density. Sometimes I have, I think, seen this the word envelope density also. Slightly different situation, but very, very similar to this. Right. Now, according to the law of large numbers, we know that as n goes to infinity, this quantity converges to the expected value of this quantity. Actually, I should have written here g of simple xi and f of simple xi instead of capital Xi, because capital X we use for the random variable. What we are looking at here is, if you, of course, if you are using uh, an estimator. If you're writing an estimator, this is the estimator. In that case, estimator is a random variable. But if you're talking about an estimate, in that case, it's better to write out g of simple xi divided by f of simple xi, where simple x's are the observations, real observations. Capital Xi is the random variable, right? So this is the estimator. Yeah, it says this is the estimator of y. Yeah, that's correct then. Right. So each of these x1 up to xn should be IID with density function fx. Then in hat will be converging to I almost surely according to the law of large numbers. Right. So now let us look at, but because we have this estimator, we know that the mean is converging to or this estimator is converging to the parameter that we want, right? It's converging to the parameter that we want to estimate. But of course, converging to that parameter is not enough. For example, if the sampling distribution, when if you consider a finite value of n, for that estimator with that sample size n, if the variance of that estimate is large, it's not very good, even if the mean itself is equal to the parameter. If the variance is large, a particular estimate that you can get has a high probability of being quite away from the parameter of interest. So therefore, it's important for us to make sure that the variance of the estimator is small as well. So therefore, let us look at the variance of this estimator. Variance of this estimate. So you can see that because this is a sample mean, right? We know that the variance of a sample mean is equal to 1 over n times the variance of the random variable. So the random variable that we are considering here is this quantity. So therefore, the theoretical variance of this quantity should be equal to 1 over n times the variance of this random variable here. So variance of in hat is equal to 1 over n times variance of gx over fx. Of course, you can see that when n goes to infinity, the variance will go to 0. But practically what we have is not n equal to infinity situation. No? What we have is a finite n. N can be very large, but it's finite. So what we want to make sure is at that n, variance of in hat is small. So how can we do that? Right? So that's what I told that I will mention later at the beginning. A good choice of fx should resemble the shape of gx so that the variance becomes small for finite n. Right. So this fx has some kind of similarity to the function that we want to integrate gx. Of course, not exactly equal, but at least for a part of that, part of x values, fx is roughly equal to gx. That's better than taking any arbitrary fx. Right. So what happens if fx is equal to gx, at least for some x values, then that for those x values, this will be almost constant. So therefore, that will make the whole variance of that random variable small, right? You know, variance of a constant is 0, of course, but this is not going to be exactly a constant, but roughly a constant if gx is approximately equal to fx. So it's going to be roughly a constant random variable, and therefore the variability will be small even if n is not infinite, right? So if fx is approximately equal to gx, then this quantity is nearly a constant over an important region of the integration. As I mentioned, it may not be equal for the whole range of integration that we are interested in, but at least for an important range, if it is uh, roughly equal, that will be much better, right? Because then we will be able to say that we are very confident that our estimate is going to be close to the actual I that we want, right? So let us now look at one or two examples where we are considering improper integer. Right. So here I'm considering gx to be sine x over 1 plus x to the power 6. I want to integrate that gx from 0 to infinity. I got the answer to this thing again using an online integer calculator, and it gave me this answer here. So this may not be the exact answer, but this is up to certain decimal places. We will take it as the approximate value. Sorry, it will take as the actual value and see what we get as the approximate value using the Monte Carlo simulations. Right. So in this case, gx is this function. So the important question is, what density should I use? Of course, theoretically, you can use any density in the interval from 0 to infinity. But as I mentioned, because of the concern regarding the variance, it's better to select a density if possible to be as close as possible to this function in at least a certain subset of the this interval here. So therefore, let us look at, first of all, this function, because in order to select a suitable density with that shape, we have to look at this function, the shape of that function. So I draw that function. I consider even though the integral is going from 0 to infinity, right? You will see that this function is going to be very high if x when x is large. Of course, sin x is going to be between some two values always. So if x is going to infinity, this is going to be going to 0, and this will be the well sin x or 1 plus x6. So gx will be will not be so gx will be actually close to 0 uh, as x is very large, becomes very large, right? Because this goes to infinity, no? This part goes to infinity, therefore the whole thing will go to 0. Therefore, it is not necessary to draw this function for the whole interval from 0 to infinity. I have drawn it for a finite small interval only from 0 to 5, just to get the idea about the function. So I consider a sequence from between 0 to 5, and I'm considering here uh, 10,000 values between those two. And this is the function sin x over 1 plus x to the power 6, right? So, and this is where I draw the function. I have actually included some other things. I will come and explain those things later. And what I do is I calculate, I first look at this function and then select a suitable density function. And then, of course, put those value of g and value of the density function. And I have drawn both in the same graph. But first, I, of course, look at g, right? So when I draw the g function, this is g, right? This black line is the gx function, right? So I have considered from 0 to 5 only. I can see that it is almost 0 here, right? So you can see that this has some kind of, what kind of shape is this as far as the density functions are concerned? There are large number of densities in the interval from 0 to infinity, right? With this positively skewed kind of shape. Now, of course, this is not a density function. This is some other g function, but it's a, uh, it resembles a positively skewed density function. So the first idea that you get is it's better to use a positively skewed density function in the interval from 0 to infinity, theoretically. Right? So therefore, what I did was I selected a gamma family. Now I want to select a particular gamma, so that that density function will be as close as possible uh, to this function. Right? Of course, that is not that easy always, because we have to select a suitable alpha value and lambda value for the gamma distribution. Right? So there are two unknowns to select, first of all. So you can use your own criteria to do that. What I did was I tried to select a gamma distribution whose mode is the same as the mode of this function. For example, this mode is occurring somewhere like 0.7, right? So one condition that I'm going to impose is whatever the gamma distribution that I'm going to use as fx should have the mode approximately at the same value as the mode of this function, like 0.7. That is one condition that I'm going to impose. And the other thing I looked at was I want the density function of my gamma to be somewhat close to 0 when x becomes 1.2, 1.5, 2, and that kind of thing, right? Close to that, more than that, the density should be almost 0. So I thought maybe if I uh, put the restriction that the 95th quantile of my gamma distribution to be 1.5 or somewhere around there, or maybe 2, even if it's possible, right? So 95th quantile to be somewhere around there. So I impose those two. So I want to find out now a density function, a gamma density function, satisfying those two conditions. The first one is the mode of that density function should be around 0.7. The 95th quantile 95th percentile, right? 0.95 fifth quantile or 95th percentile should be around 1.5 or 2, right? So for that, actually, I have to solve two nonlinear equations because the density function of a gamma distribution is nonlinear. Therefore, these two, the mode, if I say mode is equal to uh, zero point 0.7, mode is going to be a nonlinear function of alpha and lambda, and that should be equal to zero point 0.5. And then the 95th percentile is also going to be a function of alpha and lambda, but it's also a nonlinear expression. Therefore, I want that nonlinear expression to be equal to something like 1.5, right? Of course, I can find out the mode uh, of a gamma distribution with shape parameter alpha and rate parameter lambda from a book or internet. And when I found out that, the mode of a gamma distribution occurs at alpha minus 1 divided by lambda, right? So my first equation is alpha minus 1 divided by lambda is equal to zero point 0.7. So that's the same as you have to write down in this case. I'm using this library called NLE QSLV, right? And I have to write down a function uh, to solve two equations. The two equations should be written as, for example, uh, some function is equal to 0. That is one equation. The other equation also some function equal to 0. Right. So here the first equation that I want to solve is this one. The second one, the 95th quantile should be equal to, I have taken 2 here. Right. So this is the quantile is given by Q gamma 0.95 with shape parameter, whatever alpha, that is a parameter that I want to estimate. Rate should be lambda. Minus 2 is equal to 0. So these are the two equations that I want to solve, right? So when you write down this, when you write down the system of equations, you can write down the system. You have to write down the system of equation as a function, first of all, when you are solving, when you are using this function. The function that you are going to use here is NLE QSLV in this library. So when you are using this function NLE QSLV, you have to first give some initial points for alpha and lambda, as well as the system of equations that you are going to solve. So the way that you have to give the system of equation is always like that. It's going to be a function of the parameters. So then you have to say alpha is my first parameter, lambda is my second parameter. So in this case, pi will be automatically considered as a vector of two values. And then you have to specify the two equations, and then finally you have to write down them, uh, connect them by using C. So that is the general way of writing down the system of equations to be given to this function. And then you say answer is equal to uh, this function evaluated. And the two arguments here is you have to give a initial values for alpha and lambda. I have given here initial value as 2 and 1. Right. So you can also, how do you find out initial values? One easy way to do is actually something called method of moments method, which we will discuss a little later. So at the moment, you might not understand how I selected these two values, but later on, uh, when we discuss inference parts, I will explain how to select some values like that. And then function is should be equal to whatever the function of system of equations, right? And then when you solve this, you can extract your alpha, estimated value of alpha, I call it alpha hat, is given as the ANS. ANS contains several components. One component that is in ANS is ANS $X. So in this case, that quantity also has two parts because two values. So the first first component of ANS $X is going to be alpha hat. The second component of ANS $X is lambda hat. So once you get this answer, you can just type ANS. You will see there are several components. One component is named as ANS.x, and that also contains two estimates in this case. So these are the two estimates that I'm going to use in my gamma density function, right? Alpha hat and lambda hat. So what I did was, so I have here, first of all, considered some x values from 0 to 5 because that range is enough in this case. So I have got the g values here, values of g. Now I can get for the same x values, I'm going to get the density, gamma density with this alpha hat and this lambda hat. So I call it E values. You can use whatever the name you like, right? Uh, so uh, so E, I'm going calculating the D gamma, density of gamma evaluated at those capital X values with alpha hat and lambda hat. The first parameter here is the shape parameter, second one is the rate parameter. So then E will contain again 10,000 values of the density. So what I now do is I want to draw both of the graphs in the same picture. So I use the matplot command. Matplot x variable is the same for both ones, x values. So therefore, there is only x, one x, but the other one y values, there are two values in g and e. So c bind, you have to give it a c bind. And then I'm asking to use the lines to connect the points. I'm using two different types, type 1 and type 2. Type 1 is the uh, solid line and type 2 is actually the dashed line. I'm using two colors. Color 1 is the black, color 2 is red. And then X lab, I'm using X, and then Y lab GX. Actually, not only GX here, I'm showing both GX and also FX is shown in the graph. Right. So I want these lines to be a little bit wide. So I use LWD, line width is equal to 2. And I know what it is, but somebody else might not know what it is. Therefore, it's better to put a legend. So I'm going to put a legend on the top right of my picture. So these are the things that I want to write down as legend, uh, GX and FX, and then the corresponding colors and line types have to be mentioned. Otherwise, we cannot distinguish. Right. So when I run this, this is the graph that I get. Right. So therefore, in this integration, I'm going to integration of this function. I'm going to use this function, this density function, as my fx. Right. So these are the equations that I considered. Mode of the gamma, I got this expression from internet. You can easily find out alpha minus 1 over lambda. We want that to be roughly 0.7 and Q gamma 95th percentile to be actually what I had was not 1.5 in my program. I had 2, I think. Yeah. So that was I forgot to change here. So anyway, using those, these are the alpha hat value and lambda hat value. I call it alpha approximately equal. Oh, that is my alpha hat value. This is my lambda hat value. So I know now alpha hat and lambda hat. Therefore, now these are the values that I got to uh, draw this curve here, density function, right? So using those now, what I do is I first of all calculate x because I need to now get some random observations from my density. So I use x equal to r gamma n. Here I'm using 100,000 values for the random numbers. I'm using 100,000, but for the graph, of course, I use only 10,000. Even 100 is enough for that purpose. But here I'm taking a random sample. My sample should be very large. So therefore, I'm considering 100,000 here. R gamma with this n with that at alpha hat and lambda hat, where alpha hat and lambda hat was coming from this program here. So G has to be calculated at those points also. So G is equal to sin x divided by 1 plus x to the power 6. So now I have to calculate the density. Now here, these are the random numbers coming from this density function. So I have to calculate the density function at those x values. So use d gamma x alpha hat lambda hat. So then, according to what we discussed earlier, our integrand integral will be equal to approximately the expected value of this thing that is exactly equal, but approximately that will be equal to the sample mean of gx divided by fx, right? So that's why I calculate here mean of g divided by f. So that has to be my I hat. So here the answer I got is I hat is equal to 0.519, 0.519, and you saw the numerical method gave me 0.1518. So it's pretty close, right? Even this is not the exact value. I think this is again a numerical approximation. Where we have here is some kind of approximation using the Monte Carlo simulation, right? So you can see that this method works pretty well, right? As long as the sample size that you consider is large enough, right? Now here in this case, as I mentioned, I tried to get a suitable density function which roughly had the same shape, not of course equal. Gx and fx are not equal in most of the cases, but at least have the same shape here, right? It's better actually. A variance of the estimator will be small if the density function was roughly going through this thing, but that's not always possible to do that because the density function has to satisfy certain conditions. No, the whole area under the curve must be equal to one, right? Where the area under whatever the function that we want to integrate doesn't have to be equal to one. So therefore, it's not that easy to select a density function which will be approximately equal to the gx for the whole range. Right. So just to show this fact that I considered a different effects also, right? So in this case, I considered the exponential distribution instead of the gamma shape. You know, the exponential distribution is of always a completely positively skewed, right? So I'm going to consider an exponential distribution with some lambda. So in order to select lambda, I'm going to consider the tail area, right? So I'm going to assume that the tail, because first of all, when as in the previous case, you can see that this function g becomes zero, almost zero around two, right? So it's better maybe if you consider an exponential distribution, it will be coming down like this now. So therefore, I select lambda to be so that for example, 95th percentile of that exponential distribution to be around 2, like that. So in that case, I have only one parameter to estimate. Therefore, it's enough to consider one constraint, right? So therefore, what I did was I considered the same AB range just to draw the graph. I have already considered previously. So I'm going to consider that. So G is this. Uh, in this case, I have to solve one equation to find out lambda. Right. What I'm going to consider is a non-linear equation, of course, but only one equation. That is the 95th quantile of the exponential distribution with parameter lambda should be approximately equal to 2. That's what I'm considering. So here, therefore, I have in my function, I call it G lambda in this case. It's not a system of equations, it's only one equation. That equation is Q exponential quantile of the 95th quantile of the exponential distribution minus 2 should be equal to 0. So that is the equation that I'm going to solve. It's a function of lambda. So here I use in order to solve one equation, nonlinear equation, you can use the R function uniroot that you can use is a function that you can use to solve one nonlinear equation. So here the root will be directly given by the function. So I call it lambda hat. Lambda hat is equal to uniroot. In that case, you have to give the function that you have to solve, g lambda, and then in which interval you are going to look at the root. For example, if you have a uniroot, single root, of course, that function should cut off the x value, x-axis at some point. So that is the root, right? So that point has to be in some interval. So in order to run this function in root, you have to specify some initial interval. So I consider this interval as my initial interval, right? Yeah, actually, what happens is when you take the uniroot function, if you ignore this part, right? If you ignore that part, uniroot output will contain again several components. One component of that is actually root, right? There are several other components given by this function uniroot. So what I call the lambda hat is equal to actually that component coming out of the output. So uniroot, this thing will give you several outputs. Out of those components, I select the root component and call it lambda hat. Right. So now I want to show is that the original gx function and the selected exponential density function with this lambda hat value. So I calculate my density function uh, dx exp at these x values with this lambda hat value. So I have my G value and the E value. So again, use matplot to get the graph in the same picture. So you can see that now, of course, this density is approximately equal to G, at least in this part, at least in this part, right? So that's probably a better approximation than the gamma density, even if it has the same shape. As far as the two functions are considered, this function may be better because it's at least roughly equal to the integrand that we want to consider, at least in a part of the integral range of integrals, right? So if I do the same procedure with this density function, my answer becomes 0.516. So earlier it was 0.519. Now 0.1516, right? Of course, if you take a different random sample, right? If you run this same function with a different random sample of 100,000 values, your answer is going to be different, but still going to be very close to this. Several decimal places at the end will be different, right? Because this is based on a random sample. Now we are calculating gx divided by fx, the mean of that, calculated at 100,000 randomly sampled observations coming from fx, right? So as the sample changes, of course, the estimate will be different, right? But estimator is the same, but estimate, as you know, in not only in this situation, in any other situation, estimate is going to be different from sample to sample, right? So that is the very basically what this method is, Monte Carlo simulation method, based on the law of large numbers to get an approximate value for an integer, right? So now let us look at kind of advantages and limitations of these methods. These are not very serious ones. Of course, advantage is good because you can use this method to get the value approximately of any integrand. So that is a good advantage. And we saw that using the examples, the answers are pretty close to the actual values. Of course, this method can be extended to multidimensional integrals also, right? Here, what we looked at is single dimensional ones, but multiple integrations, right? Also, you can apply the same method. Uh, So the advantage is, of course, as I mentioned, this method will be useful mainly when you cannot calculate the integration analytically, right? Even if you can calculate analytically, it might be very difficult, right? In that kind of situations, also you can use this. And the other advantage is, according to the law of large numbers, we should get a pretty accurate uh, estimate if the sample size that you consider is very large, right? Because when n goes to infinity, the value should converge to the actual integration theoretically, right? So those are advantages. What are the limitations? Well, especially if you are considering this for multiple integration, convergence may not be that fast, right? Very slow, and therefore calculation might take some time. But of course, for these examples, it didn't take at least a fraction of a second. Very, very quickly you get the answer. One disadvantage is, of course, the answer that one person get may be different from the other person's get to the at the end of the several decimal places, of course, because it depends on the sample he or she used. So results vary randomly from run to run, right? That might be considered as a limitation, not a practical difficulty or weakness in most of the situations. The other thing is large sample sizes are required. Of course, it's not difficult nowadays with very powerful computers. It's not a big problem, right? Or even though it might be considered as a limitation under certain conditions, right? So that is the end of this lesson. Uh, so this is something that in the book, that is in the book as mentioned as a advantage of this particular method, for which actually I don't directly agree with. But of course, many people use this. For example, Monte Carlo integration transforms integration problems into expectation problems using random samples and law of large numbers. Difficult integers can be approximated numerically. For finite intervals, uniform random variables are convenient. For infinite intervals, distributions such as the exponential distribution are more suitable. Okay, no, this is not the one that I mentioned. Actually, in the book, there is a paragraph saying that this method can be applied directly as it reads, can be applied directly to find out confidence intervals for expected values and test hypothesis regarding expected values and so on, which is not really correct. But this fact is correct actually. This is true. Right, we have already seen this. Monte Carlo integration transforms integration problems into expectation problems. Right, so we write down the integration as an expected value, as you saw already. So, using the random samples and the law of large numbers, difficult integrands can be integers can be approximated numerically. Pretty good approximations can be obtained. For finite intervals, uniform random variables are convenient. For infinite intervals, distributions such as exponential distribution are more suitable, right? So in the examples also you saw that uh, why is it suitable? Because the variance of our estimator may be smaller. We could have actually checked that also using simulations. We will do that later, right? So we will look at the variations of estimator when we are using the gamma distribution, and also the variance of the estimator when you are using the exponential distribution. Actually, we could have tested that, checked it. And of course, we will see that the variance of the estimator when we are using the gamma density as fx may be larger than the variance of the estimator when you are using fx as the density of the exponential distribution, right? So therefore, the second estimator may be better because that estimator, corresponding estimator, has a smaller variance, uh, right? So we can be more confident that the estimate that we get using the second estimator is close to the actual value than the first estimator with a high probability, of course, not individual values. As in terms of probability, we can talk about like that. Okay. Okay, so that is the end of this lesson.